Next speaker is Erik Curiel, please.
Is there a... So first of all, I want to thank Lev for strong-arming me into coming and giving a talk today. I've mentioned, I don't remember who I was talking to earlier, but I've actually spent most of my professional life trying as hard as possible to avoid quantum mechanics. I worked mostly in space-time theory, in semi-classical gravity, black hole thermodynamics. You know, that's quantum in some sense. But the measurement problem is just too hard, I think. And so I try and be intellectually conscientious, and I've struggled and I fought against it, but I think my work in semi-classical gravity has driven me kicking and screaming to finally be forced to confront the measurement problem and interpretations of quantum mechanics. So that's what I'll be talking about today to some degree. I'm not going to be talking about semi-classical gravity or black hole thermodynamics, but I will be talking about quantum phenomena in curved space-time and how whether one can easily accommodate what some things one wants to try to say within the many worlds interpretation. So the framework is going to be, I'm not dealing with quantum fields. The framework is particle-like quantum systems propagating in a curved space-time. Sometimes we'll treat these particles as test matter. They don't source curvature. They don't contribute to the stress-energy tensor on the right-hand side of the Einstein field equation. Sometimes we will treat them as sources of curvature, as contributing to the stress-energy tensor. There are, I think, many really deep foundational issues about superposition and entanglement for such systems that really have oddly gone untreated in both the physics and the philosophy literature. Because I think they're really important, given that we think we live in a curved space-time, and we think there is quantum superposition and entanglement, even for quantum particle-like systems propagating over cosmological distances. Think about cosmic rays. And I think that these foundational issues relate both to many worlds in particular and to quantum mechanics more generally. And I want to apologize for two things, actually. One is for the roughness of some of the slides. I actually, just in the last 2 days, I drastically rewrote the second half of the talk based on discussions I had not too long ago with Harvey Brown and more recently with Simon and with David, and actually on some questions that I was inspired to think about by Alyssa's talk. And so I think I've actually now made the second half of the talk more interesting and more directly relevant to the conference. We'll see. In fact, what I'm calling the second half of the talk has almost taken over the entire talk. And what I had originally decided to talk about, I actually am going to postpone, even though it is physically these slides are the first half of the talk. I'm going to skip over those, talk about the second half stuff, and if there's time, I'll return and talk about the first half stuff. If that's clear at all. If not, then just wait and see. Oh, thank you, Tim. So the first half, which I will not be starting out with, is space-time curvature, entanglement, and Bell correlations. Incredibly interesting, really puzzling, but putting it off for the moment. So let's instead talk about space-time geometry, superposition, and many worlds. There's an ambiguity, I think, in the idea of location, for instance, of a self. Where is a self located in a branching structure? And there's an ambiguity in the idea of location and in the idea of branching itself. I think in many, most, maybe almost all, in fact, discussions of many worlds, people, I think, are really quite cavalier about how what happens with space-time in branching. Not everyone. Some people are more careful than others, and for some people, I think it's not a matter of being careful. I think, or not careful. For some people, I think they believe that they can segregate those kinds of worries, and they are probably quite often justified in doing so. But I think, nonetheless, I think it really behooves us, at least sometimes, to try to think about this. And prima facie, there are two options. And again, I really liked Alyssa's talk because I thought I think she put her finger on the ambiguity that I'm pointing to in a really clear way, although she didn't explicitly discuss it. The two possibilities are space-time itself branches at a branching event. So there are multiple copies of space-time. Bob doesn't split when Alice performs distant measurement. Rather, he is now co-located in both space-times. I think that's something that Lev and Kelvin would say. Correct. I know Lev will correct me if I'm wrong about that. The second option is only the matter fields, in some sense, branch while remaining in one gen-identical space-time. Bob splits when Alice performs a distant measurement. There are two copies of him in the same space-time. Although the way I've sketched it may make it sound as though this dichotomy rather neatly maps onto, I set the timer for myself, damn it. Rather neatly maps onto two of the primary schools of thought about many worlds, the overlap view and the efficient view. It's actually not clear to me that this dichotomy neatly maps, the dichotomy I'm pointing to with regard to the possibilities for how to think about space-time neatly maps onto the dichotomy between fission and overview. It may, I haven't thought deeply enough about it. I'm not enough of an expert on these matters to really have a firm opinion about it. I'd be curious to hear what you all think. But what can either option mean? On the face of it, at least for me, I was trained as a classical general relativist. I've spent most of my time, my professional life, thinking about matters that at least tangentially have to do with space-time issues. It's really difficult for me to get a grip on what these questions might mean. For instance, what parts or aspects of space-time and its structure are or ought to be involved in these branching processes, and how? What can one reasonably mean by space-time here, especially after a branching event? In order to try to make these questions more precise and perhaps more tractable, one certainly hopes, a man's reach should exceed his grasp, or what's a heaven for? So I'm going to rely on, I'm going to briefly discuss some recently proposed so-called tabletop quantum gravity experiments, because I think these provide a let's say relatively clear and crisp way of giving a model of some kinds of experiments one can envision where the issue of what one means by branching space-time is immediately relevant, and one can begin to really, I think, get a grip on these issues, even if not satisfactorily clarify everything one might want clarified about them. So Christodoulou and Ravelli have recently argued, I think persuasively, but I don't want to defend them in this talk, that these recently proposed tabletop quantum gravity experiments suffice to take seriously the possibility of a superposition of macroscopically distinct space-time geometries, and that really, even down to the superpositions of null cone structures, different causal structures. And I'm not going to discuss the details of the proposed experiment. I will sketch the setup and just very briefly tell you what's going on, so we have some common ground. And I'm going to assume that Christodoulou and Ravelli's conclusion is correct, and in order to investigate whether it may suggest a way to resolve the ambiguity and answer some of our questions. Even if, in fact, Christodoulou and Ravelli are wrong about what these quantum gravity tabletop experiments, if we could ever perform them, would show, nonetheless, as a thought, I still think it's valuable to use this, even if only as a thought experiment, again, because the issues are really brought out much more clearly than just trying to talk abstractly. Well, God, what does space-time branching mean? So hopefully, even if Marios and Carlo are wrong about what we will see, I think that the way they analyze the experiment is still extremely useful for my purposes. So the first part of the setup is, in fact, currently technically feasible. We have a mesoscopic particle, mass 10 to the minus 11 grams, So only, only a million times smaller than Planck mass. So really, by atomic scales, not, pretty big. It has an intrinsic spin, and it's in a definite spatial position, an eigenstate of spatial position. And we are treating it as contributing to the stress energy tensor. We're treating it as coupling with curvature. Space-time geometry, local space-time geometry is affected by the presence of this particle. We put it into a spatial superposition, for instance, using a Stern-Gerlach procedure, with the components of the superposition spatially localized a non-trivial distance apart. And then later, we're going to recombine the branches, transforming, recombining the spatial superposition back to a spatial eigenstate. I'll show you a picture in a moment. I'll very quickly just show you. So, damn it, what did I just do? Oh, good. Thank you. So here's the particle. We spatially split it. We split it into a superposition of spatially localized of eigenstates of spatially localized regions that are some non-trivial distance apart. We let them cruise forward. We leave, isolated, we leave it alone, superposition remains intact. And then later we recombine it into, we affect a unitary transformation that recombines the superposition into a single particle spatial eigenstate. The second part of the experiment is not technically feasible at the moment. It certainly seems straightforwardly possible in principle, and many very knowledgeable, eminent experimentalists think that, in fact, it's within our grasp, say, in the next 20 years. Marcus Asselmeyer actually thinks it's achievable within 5 years, but as much as I like Marcus and think he's a smart guy, I think he's a bit crazy on this one. But in any event, the setup is we introduce a second mesoscopic particle identical to the first. We put it into an equivalent superposition at the same time in the lab frame as we did the first, so that all four spatially localized components of the two superpositions lie in a straight line, such that the closest spatially localized components are mesoscopic distance apart d on the order of 10 to the minus 4 centimeters. And they remain so. We allow the superposition just to evolve in otherwise isolated circumstance for approximately a second. And these numbers, I'm not going to get into why these exact number values are relevant, but just believe me or not, that these are good numbers for drawing the conclusions that Marios and Carlo want to draw. And so, again, here's the setup. Now, the complete setup. We have our first particle. We have the identical second particle. We put them into superpositions at the same time in the lab frame. The spatially localized components of the superposition on the right-hand side of the first particle and the left-hand side of the second particle are this smallish distance d apart during the free evolution of the system going forward. The other distances, and this distance is small enough that there will be a non-negligible gravitational influence of if these were just two ordinary particles, ignoring quantum effects, there would be, by the acuity that the experimentalists are proposing, there would be non-negligible gravitational interaction between these two, but completely negligible gravitational interaction between that branch and this one, that branch and this one, that branch and this one, and so on. So one expects entanglement to develop between the two particles due to, I'm being very imprecise here, but not, I think, I hope not in a pernicious or misleading way. I think we all know what I'm talking about. I can write down a lot of equations. I don't think that would actually clarify anything. I'm hoping that just saying it, and you guys can supply the equations in your head if you like to think that way. But the level at which this is, I want to hold this discussion, I think, is at a high enough level that I think it should be clear without beating you over the head with lines and lines of equations. So one expects entanglement to develop between the two particles due to the rotation of the quantum state phases induced by the shift in energy of each particle from their non-negligible mutual gravitational interaction in branch 1r2l. In this branch. So we think that, speaking very crudely, when we have put these two particles into each into a superposition, there are now 4 branches. I'm not necessarily saying branch in the sense of many worlds right now, just in a loose quantum mechanical sense. And it's this branch that is going to induce the phase rotation that will induce entanglement between the two particles. Now, the people who first proposed these experiments, Boza et al. And Marletto and Vedral, in so doing, they developed information theoretic arguments that such entanglement can be mediated by a physical entity, in this case the gravitational field, only if that entity is itself a quantum system. Christodoulou and Ravelli call this the BMV effect, which I think is a little unfair to the et al. It should really be like the BEMV effect, but let that go. And Christodoulou and Ravelli further argue to explicitly conclude, and I now quote from their paper, the BMV effect counts as evidence that quantum superposition of different classical spacetime geometries is possible, can be achieved in the lab, and has observable effects. So during the period when there were 4 branches, 1R2L, 1L2L, 1L2R, 1R2R, there is a quantum superposition of 2 classical spacetime geometries. The one where things are shifted due to the non-trivial gravitational interaction between the left-hand side of particle 1 and the right-hand side of particle 2, and the spacetimes that are otherwise unaffected by the presence by the gravitational interactions of the masses. When the particle superpositions, these branches recombine, returning to position eigenstates, the spacetime geometry does so as well. So let's consider what I called option 1 earlier, spacetime itself branches. There are 2 copies of the entirety of spacetime during superposition. They recombine back into 1 when superposition is recombined. I have absolutely no idea how to understand this. I'm really just putting this option aside. If someone can tell me a way to cogently think about this, I would love to hear it. Option 2, I think, so option 2, only matter fields branch. I think there actually might be a way to begin to make sense of this in this picture. Because at least the way that I think about space-time geometry and general relativity, the metric, the affine structure, these are all physical fields. These are physical parts of the world. So only matter fields branch. Well, then space-time, at least some parts or aspects of space-time geometry can branch as well. So there are 2 copies of parts of space-time geometry, whatever exactly that might mean. I'll return to that during the superposition. And they recombine back into 1 when superposition is recombined. And as I say, I think I may have a way to begin to try to understand this, but this is extremely, now we're moving into really speculative and vague territory, and I'm going to be making some proposals that I have no desire to die on the hill for any of them, die on any hill for any of them. I'm really just throwing ideas out and hoping that y'all can really help me with this. So on the decoherence branching picture, the kind of thing that Simon and David and others have developed, the splitting spacetime geometries are presumably effective descriptions, presumably emergent from some presumed underlying structures of a quantum gravity world. A lot of presumption going on here. Only those parts of the total classical spacetime geometry that's non-negligibly affected by the changes in the matter distribution, say the causal or the null cone structure, the affine structure, the metric structure, but probably not the differential structure or the topology, okay. Maybe, are in an effective superposition locally. And by locally, I mean the space-time region that's really affected by the superposition of the matter distribution, because of course in general relativity, it's not Newtonian gravity. When Newtonian gravity, when I wave my hand, I with just sublime virtuosity change the orbit of Saturn instantaneously. But that doesn't happen in GR. Quote unquote gravitational effects propagate at most with the speed of light. These localized superposed parts, superposition of null cone structures, superposition of affine structure, spread out from the branching event with speed determined by the decoherence process, in this case presumably speed of light, since the decoherence process will be mediated by the gravitational interaction. And this is actually the final slide, because with that unbelievably vague proposal, I now have a whole bunch of questions that I think need to be addressed in order to try and see whether this unbelievably vague proposal can be given anything like a chance of being made clear enough to try and judge whether it's a good proposal or not. So first question, after recombination of superpositions, do the previously localized superposed parts of spacetime geometry continue to propagate outward in some sense? If parts of local geometries can branch without the entirety of spacetime structure replicating itself in new branches, how do the branched and unbranched parts of spacetime structure relate to each other? Does, for instance, only the Ricci part of the curvature tensor branch, wow, I can't speak. Does only the Ricci part of the curvature tensor, of the Riemann curvature tensor branch, while the Weil part doesn't, since stress energy couples directly with Ricci, point by point, but not with Weil. If that's the case, though, then how can the causal structure branch, since the causal structure is encoded in some way in the conformal structure in the Weil tensor? But the Weil tensor is sensitive to the foregradient, in fact, of the stress energy. Even though point by point, it's independent of stress energy distribution, the Weil tensor, the divergence of the Weil tensor actually is proportional to the foregradient of the stress energy tensor. And so spatially localized matter, which by uncertainty principle has non-trivial momentum spread, presumably induces some kind of quantum fuzziness in the conformal structure in each branch, because momentum is part of the foregradient of the stress energy tensor. So how is that in some sense, is this quantum fuzziness in some sense consistent with the splitting of the causal structure? There are delicate but rigid relations of interdependence between levels of space-time structure and classical GR, for instance, between curvature and topology. They place non-trivial constraints on each other. How is one supposed to make sense of these relations during the branching if only one level of structure, say curvature, branches, but not the other? Topology doesn't. It doesn't seem that the usual position basis in the decoherence analysis can serve as the privileged decoherence basis here when space-time structure branches, because position becomes ambiguous. So can one make sense of a decoherence basis in this process at all? If so, what is it? And how about when recombining branches? And on that unresolved dissonance, I end. Thank you. Someone speak. Come on. Oh.
Okay. So I mean, there's lots to ask about. Let me pick one piece here. I mean, I think as an interpretation of how I read most of this literature, I sort of think the technical answer which I think you're going to hate, is much more flat, and I think you kind of probably know that really, is kind of much more flat-footed than this. It's just that we're linearizing around the background and treating G as a spin-2 field. I think that's fine, incidentally, but I think whether or not it's fine, that looks like the right reading of how most people in this literature are doing it.
So you are right, I do hate it. Let me say maybe one thing about why I hate it for those in the audience who I have not talked with about this. So it's not clear to me that even even in this very simple case with these mesoscopic with these mesoscopic masses and mesoscopic distances, that the linearized treating the metric perturbation as linearized spin-2 will actually will really give you what you want. It actually, so it is, to be fair to your suggestion, it is the case that in most of these arguments, the conclusion that we get a superposition of classical geometries is in fact derived by looking at perturbative quantum gravity and looking at the leading order graviton contribution. But I'm a geometer, man. I'm not an algebraist, and I want to understand So I don't want to reject your answer. I think that's absolutely an interesting possibility to explore. But as a geometer, as a relativist, I want to understand how this works geometrically. And in the end, it may in fact be the case that there is no good way to think about this geometrically, and we really are forced to think about it solely in terms of first order linearized quantum gravity and spin-2 fields. And if so much the worse for my love of geometry. But I hope that's not the case.
Let's talk more offline.
I think this may connect, although I'm not deep enough into it to understand to what David said. But I mean, one way of looking at this, at least that occurs to me, is that there's a conceptual problem putting together the problem you want to set up, even with your first diagram. You want the particle to be heavy enough to have a non-trivial effect on the space-time geometry. But in the diagram, you split it from a position eigenstate to a non-eigenstate. But then you say, I recombine it. Or what the hell does recombine mean? I mean, now we're back to the whole problem or something. I now have, as it were, this branch propagating in one space-time, that branch propagating in another space-time. I don't even know what it means to bring them back to the same location and recombine them. But if you can't make sense out of that, then a whole bunch of the other argumentation that talks about recombination and, getting rid of the space-time, uncertainty or whatever, no, you can't make sense of that. And I do think we're kind of back to the whole argument, do I want to identify points in a non-metricized, purely topological, blah, blah. I mean, don't you think all of that has to be addressed to make sense of the setup here?
Absolutely. No, Tim, I'm in the uncomfortable position of agreeing with every single word you just said.
Okay.
No, I think you're absolutely right. That is an enormous question that I didn't mention, but that absolutely needs to be addressed.
Okay, so I want to just make a comment, and it's not really coming from me, because I don't know enough about gravitation, theory of gravitation, to really comment on this. But for the last few weeks, I happened to be visiting Ron Foldman's lab at Ben-Gurion University, where he's actually planning to do these experiments. And he invited Sugato Bose and others to come and to have conversations and so on. So I asked Sugato Bose, do you assume no retrocausality? And he said, yes, that's very interesting, we do. Do you assume retrocausality?
So for the,
No
for...
retrocausality, sorry.
I don't see anywhere in the argument that that Boza and the other people make where retrocausality would necessarily screw things up. I can imagine making it screw things up, but I don't see that it would necessarily screw things up. And I think that the same is true for the Christodoulou-Ravelli argument that I'm relying on. They don't invoke retrocausality, and I think that their argument would go through if there were certain mild forms of retrocausality allowed. It certainly is the case that if there were some extreme, what a lot of people would say pathological kinds of retrocausality were allowed, then their argument would definitely not work.
Yeah, a couple points. First of all, I might remind you that actually my undergraduate advisor, Don Gilkert, I actually did an experiment to rule out the semi-classical gravity with these massive balls in position. But of course, that didn't have the coherence thing. But I just wondered in this case, I mean, it should be, I would think it would be pretty analogous except for the ratio of the forces if you just had charged particles. So has that been done? Put charged particle going around there, and or does the charged particle just interact so much with the environment that you can't, with the rest of the environment that you just can't do these? I don't know. Is it possible to do it with charged particles?
So it's certainly. I mean, I'm not an experimentalist. I see no reason whatsoever why it couldn't be done with charged particles, but the reason why they're interested in doing it with a gravity-mediated interaction is because the idea is that they want to be able to show that gravity must be quantized. It's, there are still some people around who, at least for the sake of argument, and I have some sympathy with the desire to push this idea as far as possible, who say, you know what, I've never heard a really, really compelling argument that we have to quantize gravity. Let's just stick with quantum fields and curved spacetime. And the idea here is that if we can show that a process that is mediated only by a gravitational interaction can induce entanglement between two unquestionably quantum systems, then that, based on these information theoretic arguments, must show that gravity itself is a quantum phenomenon, is a quantum system. The gravitational field is a quantum system, because only quantum systems can induce entanglement between two other quantum systems. So that's why they're dealing with gravity in these experiments. I think that the charge case you're talking about would be fascinating to do, but I don't know whether it's been done or people have thought about doing it.
I agree that gravity is conceptually much more interesting, but it's not quite clear to me, in the charged particle case, that it shift the fringes in the two-sided or becomes sufficiently decoherent that you don't get, well, I suppose it decoheres in some sense. Well, anyway, it'd be interesting to see what, and then you can compare the gravitational result to some actual experiment.
Well, that's exactly so. Those concrete numbers I was throwing in, 1 second and 10 to the minus 5 centimeters and all that. That actually is done precisely to try to control for complete decoherence. That's like those are the maximum numbers you can use, at least according to theoretical calculations, where you can avoid complete decoherence.
Thank you very much.
So just to remind what will happen now, as usual, we are supposed to be kicked out before, which was promised. So we'll have a coffee break, 20 minutes. We'll have one talk. We'll have probably very short open discussion on the topics which just discussed before. And the announcement really for poster presenters. Immediately after this discussion, there will be recording of posters. So think about a few minutes explaining what is going. So we'll have camera, we'll go from one poster to another, and the presenter will explain what is there. All this will go to in parallel with lunch and with kind of a poster session, which all this is supposed to happen.